Let's now consider another counting problem. 13 cards are dealt from a well-shuffled deck. Let X denote the number of hearts that appear. Find the probability of 3 hearts. Find the expected number of hearts as well as the standard deviation for the number of hearts. For this one, we notice that this is drawing without replacement. We're dealing cards off a deck without putting them back into the deck. And so this is an example of a hypergeometric distribution where I'm choosing, there's 52 cards, of which we choose 13 but without replacement. Just we pick 13 cards and leave alone the other 39. There's no possibility of being dealt the same card twice in a row. So for this one, it's hypergeometric, and so the probability is going to be as follows. The probability that X is equal to 3. Following the notation that was used in class, and you also find in the book, the notation is that this is going to be h of 3, where I have the following parameters. I have 13 draws. There are 13 hearts in the deck out of a total population of 52. Personally, I find that a little cumbersome to remember, and the way that I prefer to remember this is just simply writing down the combinatorics, or the binomial coefficients. So there are 13 good objects, so to speak. There are 13 hearts, of which I want 3. There are 39 bad objects, everything that isn't a heart, and I need 10 of those to get a total of 13 cards drawn. And there are 52 total cards, of which 13 are selected. And then it's just a matter of computing the binomial coefficients. This can be done with factorials, or more simply with the dedicated number that is found in most calculators. And we get an answer of 0.2863, accurate to 4 decimal places. So that's the answer for part A. To find the expected value of X is going to be equal to n times, basically n times p, n times the number of good things over the things that aren't good. So basically n times p, which is the same formula that we had for the binomial distribution. We have 52 total objects, back up. We have 13 objects that are being drawn, and the probability of drawing a good one is 13 over 52. And so the chance of the expected value for the number of hearts that gets drawn is 13/4, or 3.25. That's something you probably could have guessed before taking this course. Somewhat trickier is the standard deviation of X. And the formula for this looks somewhat similar to the formula that we had before. Square root of n times p times 1 minus p, as before. So this matches what we had for the binomial distribution. But because it's hypergeometric, the data will be a little bit less spread out, and the way of quantifying how less spread out it is, we multiply by this finite population correction factor. So at capital N minus little n, it's supposed to be an n, capital N minus little n over capital N minus 1. So in our case, that'll be square root of 52 times 13 over 52 times 39 over 52. So that's the first part. And I made the same mistake again, so let me correct that. The little n is in front, so this should not be 52 here, so I'm sorry about that. Little n is 13, the number of draws, times the probability of drawing a heart, times the probability of not drawing a heart, times the population correction factor, which is 52 minus 13, divided by 52 minus 1. And so plugging that into a calculator, we get the standard deviation, which is 1.3653, accurate to 4 decimal places. So that is the computation of the probabilities, the expected value, and the standard deviation for the hypergeometric distribution.